Hi. So,
Hello.
Mr. Bilgic is a physicist and electrical engineer by training. He is now the CEO of KROHNE, and as well he is the head of the VDE community of measurement and automation technology. So very well known and experienced in our field of interest. And I am very happy to introduce him as being the keynote speaker for the opening lecture, and he will take us actually on a path, and that will give us insights into getting from data to knowledge. And I hope that you will accept me and us as hitchhikers on your journey onto the path. So, Mr. Bilgic, the floor is yours.
Thank you, Tobias, for the very nice and kind introduction. So it's actually a big pity that we can't meet in Copenhagen. I would really love to meet many of you in real life and not just online. I'm pretty sure I know many of the audience here also personally. Yeah, but we still have good hope that it will happen in the next opportunity. I would also like to thank the organizing committee for inviting me for this keynote. It's very much appreciated, and I hope I'm able to take you with me on to my journey. So what I prepared for you is an overview of what I called the eightfold path, and please follow me along that one. So what happened? One day I stood in my office and I was facing dark matters. I saw a lot of data and asked myself, how can we extract information out of it? Something we can really use. Or even more important, how can we create knowledge? Real understanding of what we do. With so much data, an almost infinite amount of data, it looked like a terrible mess. But then I turned to the window and a rainbow showed me the way. I saw the clear answer immediately. It was the number 8. I just had to follow the eightfold path. And then I stood back and I saw the following. What we have to do is we need right awareness, right preservation, right connection, right protection, right context, right modesty, right focus, and finally right sharing. And what this is all about in the process industry, we will see now step by step. The first thing is you have data. Actually, you have lots of data. And where that is coming from, I will show you exemplary on one of our KROHNE devices. Let's look at the Coriolis mass flow meter. The Coriolis mass flow meter is providing very accurate measurements of mass flow and also density. And it can actually do so quite precisely, and it's known for decades. What we extended is that we made it able to measure entrained gas and compensate for its effect from 0 up to 100%. And that's since 2012. So this is the primary data you see when you look at the sensor. But there is a lot more behind it, and you will see it when you look inside. So once again, when you look at the process quantities, you see flow, you see density and temperature. But what is actually measured inside the device is a Coriolis time shift, a resonance frequency, and a PT500 resistance. And from those 3 quantities, you can calculate a lot of other quantities like mass flow, like volume flow, or density and concentration, or even the concentration flow, and of course the temperature. But additionally, there is more information in the device. There is process diagnosis available. like physical quantity under or over range, or even multi-phase flow information. And of course, in the electronics, there is a lot of self-diagnosis available, like for temporary processing, internal value under and over range, internal communication, CPU and RAM tests, electronic temperature, and so on. So there is a lot of data, and actually there is a lot of information already available today. Let's look at the next step in our eightfold path. We have a lot of data, but we need right preservation. And it means do not convert your data away. And what I mean by this, I will show you in an illustration from a German fairy tale, Hans in Luck. I think you may know it. Hans in Luck got a lump of gold, and whenever he meets someone, he's exchanging this for something else. And then the something else is again exchanged. And so on, the value of his lump of gold becomes less and less until he ends up with 0. Sounds like a fairy tale, but that's pretty much what we do actually today in our installation in the process industry. Let's look why. What is common practice today is that we have a lot of equipment already in the field. Sensors, measurement technology, actuators. We connect them via a 4 to 20 milliampere loop through a remote I/O with a control system. Let's more specifically look at a little part of a big plant. Let's look at a control loop. For a control loop, we need a valve to control the flow, and we need a flow meter to measure the flow. The flow meter is indicating the flow, giving the information to the PCS, and then the PCS in turn is controlling the valve to open up more or to close more the flow. Theoretically, it's quite easy, but what's actually happening is the following. In the flow meter, we do an analog to digital conversion from the actual flow primary measurement in the electronics. There we do a lot of complex digital analytics. We'll come to that later. Then we do conversion from digital to analog to transfer the flow measurement value via a 4 to 20 milliamp power loop to the remote I/O. And this is growing through hot and cold areas. You can imagine it has to work somewhere in the North Pole as well as somewhere in the desert. Typically in the remote I/O, we do an analog to digital conversion again, and then we transfer the signal to the PCS. There, some digital calculation is done of a new valve position in our example. Then it is again converted from a digital signal to an analog signal, transferred back via a power loop. And then in a valve, in the electronics of the valve, the analog signal is again digitalized and used for some digital processing. A new adjustment value for the valve positioner is calculated, converted into an analog signal, and then transferred to the positioner. That's quite a lot of conversions. But I have another example to show it more in a simplified way. If you're a hobby photographer and you have a digital camera and you would want to send one of your pictures to your friends, family, then this example will show how you usually should not do it. You take the picture with your digital camera, you print it on your printer, you take the print from the printer, move on to your scanner, put it in the scanner, digitalize it again, scan it, bring it to your PC, and then send it via email. I think that really sounds weird to you, and probably no one of us would ever do it in such a way, but that's, in a simplified way, what we actually still do in the process industry. And I think there's really room for improvement. Another example to illustrate what we actually do to the possibilities we have, or how we underuse it, was presented by Dr. Broker in one of the NAMO general meetings. I think it was in 2014. He made a very nice presentation on the accuracy of flow meters and the reality check. I don't want to repeat everything here, but I just want to focus on the main aspects. We as manufacturers, we specify measuring accuracies under certain conditions. And of course, the information is spread in the technical documentation. But what are the main factors influencing the additional errors? And this is actually the influence of the medium temperature. There is influence of medium pressure, of the ambient temperature, the 0-point stability, the use of the current output actually, and the influence of signal processing, the supply, insulator, I/O input cards, and so on. And he looked at two simple examples. He took a Coriolis mass flow meter, typical high-end device, which is specified at 0.1% accuracy. And we consider two cases. Case one is under normal medium pressure and at 50% of the measurement range. That is a turn down ratio of 1 to 2. So we use the scale quite nicely. But the other example is with 10% of measurement range, and it means it's a turn down ratio of 1 to 10. That means we're going quite to the beginning of the measurement range. And let's only look at the error contribution in such a case. So this is the sensor, the actual sensor error under these boundary conditions. And we see the major impact on the sensor error is the ambient temperature. It's dominating all the other errors. But next to the actual sensor error, there is an error contribution from power supply. And another one, a significant error contribution from the analog input to the SSPC. So that the total error in that case would amount to 0.55%. Remember, the specified accuracy was 0.1%. When you look at the second case, turn down ratio 1 to 10, again, going to the lower end of the measurement range, then you see that the ambient temperature contributes even more to the sensor error, amounting almost to 2%. And the power supply and also analog SSPC input give major contributions to a total error bigger than 2.5%. So that's quite significant. And it shows that we lose a lot by the many conversions, signal conversions and processing we do in our systems. So the summary by me of that is we have to go more digital, because digital will reduce the ambient temperature effect in the sensors itself. It will definitely contribute to a lower actual sensor error in such systems. It will reduce the power supply impact. It will eliminate the analog input error to the SSPC and results in a much smaller absolute overall error. So that means we have not to convert our data away. That's actually what we do today as PT. The next point is looking to the right connection. And for that, we have to use suitable technologies. Maybe some of us might remember the good old times for the telephone system. When you wanted to call someone, especially someone overseas, there was an operator sitting somewhere and physically connecting the caller and the receiver. It actually established a physical connection between two parties. A physical connection doesn't have to be in a wire. It can be also a radio transmission in between. But the important point is it is a one-to-one connection. That's why this communication type is called circuit switched communication. It was quite stable. It is reliable once the connection is set up, but it is also very inflexible. And it really relies on a stable connection, can be wired, can be wireless, between the two parties. That's definitely not what we do nowadays, and it's definitely not how computer networks work. Computer networks actually work in a packet switch communication setup, where a sender sends packages. Packages can be routed through different ways, and will be recombined at the recipient again. such a communication network is much more reliable, it has redundancy, and it has a much higher flexibility. That's a typical setup for modern computer networks. Can be the internet itself or a subnet. Let's look what we do today in the process industry. Again, we see this is the setup as we discussed it already. We connect all our equipments through an analog 4 to 20 milliamp current loop to a remote I/O and then finally to a control system. But revolutionary, we were able to modulate a digital signal on this, and this is what we call hard communication. Besides its low speed, the hard communication is actually exactly the setup I've shown before. It's a circuit switch communication with all the advantages and disadvantages such a system brings. Point-to-point connectivity, no connectivity in between assets, yeah, and a static communication setup. So looking at that, Namur came up with the idea to extend that system. And that's what they called the NOAA-Namur Open Architecture, which actually provides a second communication channel. Why that? Because this old-fashioned, established, but robust communication architecture of the past should still persist, should be carried on to the future to keep all the advantages it brings. But with a second channel, we open up a completely new communication world with all the possibilities it brings, but we have to do it in a safe and secure manner. Now, there are actually two ways to build such a second channel. The one way is to do a kind of physical separation of your communication channels, the first and the second channel, and the other one is a logical separation. It means same physical channel, but separating by content on the logical level. I will give you an example of what that means for us in the process industry. A simple way to extend the architecture we have seen by a physical second channel is, for example, Bluetooth. Bluetooth is just an example for wireless technology. Could be also wireless LAN, it could be another technology. The advantage of this is that you can use the existing infrastructure, you add wireless connectivity, you need hubs to connect to collect the information. And as you can clearly see here, there is no physical connection between a control system, which still runs in the old-fashioned way, yeah, and the new world of big data, of open communication, where you can enhance a lot of features that is completely impossible in our closed world. That's an easy one, theoretically. Another one is the logical separation. We remove the connectivity, the Bluetooth connectivity again, yeah, and we connect our equipment with Ethernet. In that way, all the equipments in the field can go through a splitter, which then decides what is critical for the control functionality. That information is going to the PCS, and all the other additional information, the additional data that we already have in the field, is going to a cloud or on-premise solution. We'll come to that a little bit later. After looking at the right connection, you also need to look at the right protection, because it's nice to extend our world with all the open features, with all the big data approaches and artificial intelligence approaches, which is already in the world, but definitely we do not want to sacrifice operation safety. That's, I think it's a must-have. And as you all are aware, we have X zones, explosion protection zones. When we put in a lot of cabling, especially with high energy, and something nasty happens, then it results in unnice pictures, in unnice situations that we all want to avoid. So that means that the nice connectivity with Ethernet, which brings a lot of possibilities to the field, also has to be suitable to work in an explosion protected area. To do so, we have to limit the energy we use for the signal transmission in the Ethernet network. That's easy said, but that's quite difficult to be done, because we need energy for digital signal transmission. What you see here, we don't need to go into detail, is what is called the eye diagram for digital communication systems. When you have the situation like in the upper right corner, you can clearly distinguish between the ones and the zeros in the digital transmission. But when you get noisy signals, especially long cables, electromagnetic interference, and there are many other sources, then the boundary between the zeros and the ones is going to diminish. It will increase significantly the so-called bit error rate, and this makes the digital signal transmission difficult or close to impossible. Because at the other side, you have to consider that you have to bridge large distances. You need long cables, because our plants are not just fitting on a table. And that's why a consortium, an industry consortium, thought about how to extend this Ethernet standard. And they came up with the so-called Advanced Physical Layer, APL. And the mission is to find an extension to the Ethernet standard 802.3 CG, which is fully compatible for all the higher layers, and just changing something little in the physical layer. We come to that overview on the next slide. At the same time, they had to solve the power problem. Here you see the power requirement of a high performance 4-wire device, which goes up to 10 watts. Then you see here the tiny little power budget for a typical 2-wire device, which is around 35 milliwatts. And the blue box is what is extended by APL, by the new APL standard. It already looks quite nice. It is significantly more than what is available in 2-wire systems, but it also needs more power, because this is the power budget breakdown for a typical APL device. You still need something for the sensor if you take a high performance sensor. Then also your MCU for Profinet needs quite some energy, 100 to 150 milliwatt. Your physical layer circuitry needs 50 to 100 milliwatt. And of course, the XCMC circuitry also needs energy. So the 500 milliwatt typically specified for an APL equipment are easily distributed, and you end up with a low performance 4-wire device when you compare to the full power budget, what you have available today. When you look at the open system interconnection model, the OSI standard, then you see clearly what I mentioned before. APL is just modifying the physical layer here in the lower right corner. All the other communication layers on top are fully IEEE compliant, and that means all the nice things we know from Ethernet connectivity can be seamlessly transferred to a world using APL. And this modification, once again, to make it clear, was necessary to transmit Ethernet compliant digital signals on 2 wires with limited energy in an X area. So as a summary, what APL will be, it will be a new physical layer for the process industry. It is able to transport many protocols like Profinet, Ethernet IP, UPC UA, MQTT, HTTP, and so on and so forth. It is an enabler for IP-based technologies in the field, and it contributes to safety, explosion protection. But what it will not be, it's definitely not backward compatible to 2-wire, 4 to 20 milliamp loop. It is not a new protocol or even an IoT technology, and it does not solve safety and security requirements entirely, at least not yet. And it is definitely not a replacement for 4-wire technology. I hope that could be illustrated by the rectangular power areas, by the power map I've shown before. Coming back to the 2 ways, the physical and the logical separation for the second channel to implement the NOAA architecture, there is another aspect, and that is the security and safety aspect, especially when it comes to wireless connectivity. That's why we thought about a structure and architecture, how to make a SIL-compliant Coriolis mass flow meter be suitable for communication with Bluetooth connectivity. The one aspect is you have to take care for safety, and the other at the same time is you have to take care for security. They sound similar, but they are quite different. There is a simple example. For security, you would immediately want to do an update as soon as an update would be available. That's what you all know from your mobile phones, from your tablets, from your laptops, that your system is asking you to immediately install an update, if you didn't even allow it to do it automatically, as soon as a security update is available. But this is quite the opposite for safety. Your safety core system shouldn't be updated. So if there would be an update available, you should step back and say, hey, hold on a moment. I'm not going to change my certified software in my security system. So how to manage that is quite a challenging task. And the only way that we came up with to solve it is this ring structure, or this shell structure with different security layers. The outer is an insecure area with no trust without authentication. Here you connect to mobile devices. Then you have the outer secure area with partial trust, and of course the inner secure area, that's the safety redundant area, which of course is under full trust. And in between there is a firewall, and we even build in a hardware switch. The hardware switch can completely shut off any wireless communication. It can bring the system to read-only mode, or even to read and write mode. With that, we were able to get a certified security and safety compliant system for the process industry. So after we protected our system correctly, we have to think about the context into which we have to put our data and information to finally make information knowledge for the people, for our people in the field. And to do so, we have to prepare what our experts need. Let me start with a simple example. An example just shows in a very simple and superficial way how to make use of separate data streams from plants. A plant operator still wants to get primary measurement value, how we call them, for flow, level, temperature, pressure, and of course for chemical analytics. A process optimizer might eventually look at different data like chemical analysis or information from soft sensors. And the asset manager might look at device or plant diagnostic data to also give feedback to the plant operator, but in terms of predictive maintenance information. Sounds quite simple, but it's not that easy to realize in practice. Again, I want to look at a simple example from a flow meter. When you look at the electromagnetic flow meter, we don't have to go into the detail how it works here. I will quickly illustrate that. The context of the plant operator is, how can I get reliable process control data? So he wants to get a stable, reliable flow value from this instrument in the field. And to do so, we as KROHNE, but also the other competitors in the market, put quite some effort into the device to stabilize the signal. This, for example, would be a typical signal at the electrodes of the equipment or at the ADC of the electronics in a typical flow situation. We switch the magnetic field periodically to cancel out asymmetries. Yep. And we have signal overshoots due to the switching magnetic field, which we have to eliminate. And then we end up with those more or less stabilized signals, which lead to a more or less stabilized flow signal, which again goes through a filter. In this here, we have taken a finite impulse response filter, FIR filter, which is flattening out the signal variations over time and leads to a stabilized flow signal. So we're happy we got a stabilized flow signal. So far, so good. The asset manager might now ask a different question. He might look at who can I ask when the pump is about to break. For sure, you can take diagnostic information directly from your smart pump, but eventually your purchase department did some savings on the budget and you are not allowed to buy a smart pump and you have a simple unregulated pump. But your flow meter can still tell you something about the pump. You just do something different. You don't cut away all the information as I've just shown before in order to stabilize the flow signal. You just do a fast Fourier transform of the time-dependent signal, and in your spectrum, suddenly you find the pump signal. And that will tell you quite a lot about how the pump is feeling. Doing this is a different topic. Here, I just wanted to show that even in the spectrum of an electromagnetic flow meter, you will be able to see information about other assets in the plant. So you have to prepare what your experts need. The next topic is right modesty. And right modesty means we as humans, we have to accept when machines can do things better. I love this example. I've used it many times. It's actually quite old, but it's still valid. It shows the development of computing power per $1,000 because we have to do cost normalizations. Sometimes we also do power normalizations, but here we focus more on the cost. This is a obviously logarithmic scale. This is a linear scale. So that means this straight line is exponential growth. And there are just many examples of computing machines here over time. I'll pick up that slide again later. Where we are today on that line of growing computer performance and human performance, we're about here. So we are close to a crossover when computer performance can outperform us. Of course, this is not valid for everything, but this is valid for quite some things. And for what it is valid will be shown on that slide. I've taken that picture from Max Tegmark, where he tried to sketch where artificial intelligence already outperformed human intelligence. In what area did it already happen? So it means what is underwater is already taken by AI, and what is still above water or high in a mountain is quite far for AI. For example, driving is about to be conquered by AI. Go is already conquered. Arithmetic, chess, this is all in jeopardy. Even investments, there are quite some interesting tools now available which do a very clever and high performance investment, probably much better than many human investors could think about. But there are also still some other things like cinematography or art, which is still out of reach for AI. And also science is up here right on the mountain, so good for all the scientists among us. But things are developing, and we just challenged the Microsoft Azure online face recognition service. And what you see here, I just uploaded my picture, not to have any problems with copyrights of other people. And this is the answer structure of the algorithm. It gave me a 1.0 in happiness. And as you can read here, 0 anger, 0 content, 0 disgust, and so on. And I think it matches quite well. So, and then the big question is, can we use such intelligent algorithms also for other things, detecting complex situations? And of course we can. Next example I want to show you is again on a flow meter. Sorry, we are mainly a flow meter company, so that is where our core expertise is. And we wanted to look at the vortex flow meter. The vortex flow meter is illustrated here. The basic principle, you have kind of shadow bar in a stream, and behind it there are some vortices generated. And the frequency of the vortices is directly proportional to the flow speed. That's more or less the basic principle. When you look at the time-dependent signal, you see at the pickup, yeah, you would see such a line. Actually, you don't see anything, but again, you can do a fast Fourier transform, and you happily see, oh, there was one big peak in the frequency. Yes, that's your vortex frequency. That's what is used today to measure the volume flow, the flow speed through the pipe, and thus you calculate by knowing the pipe diameter, the volume flow. Quite nice. So you take exactly that point, the maximum in the spectrum, and then you remove all the other information. And that is the basic principle how a vortex flow meter is working today. But how does the situation look like in a more complex situation? A more complex could be, for example, again, a two-phase flow situation. And this is a standard diagram to classify two-phase flows. You see the superficial liquid velocity over the superficial gas velocity. And then you have, flow regimes like finely dispersed bubble, slug flow, bubble flow, turn, and annular flow. And some of those flow regimes are shown here. These are real life pictures. Again, when we look at the time-dependent signal of the vortex flow meter for the different flow regimes, you see such nice timelines. What we can do here is a so-called STFT, a short-time Fourier transform. The short-time Fourier transform makes a time-dependent spectrum of this time-dependent signal. So what you see here is the frequency, the color gives the amplitude. So you see a spectrum at a certain point in time. You see how the spectrum is changing over time. But what you see here is in the end, for an artificial intelligence or machine learning system, just a picture. And with a proper training, and that's what we already did, the machine learning system is able to identify the flow regime just by such a picture with a very high confidentiality of more than 96%. And that is already quite some more insight. Again, there is no additional instrumentation. There is nothing else done, just taking the raw data as it is available, but processing it in a different way. And of course, that can be very useful for process optimizers. We can finally say, okay, I got a deeper insight into my process. What I've shown here is, of course, just a simple example. You should really imagine that such things can be done for much more complicated and complex chemical analysis data and so-called soft sensors. There are already quite some studies available and ongoing that with a proper combination of simple sensors and simple information, especially on the base of raw data, in combination with well-trained artificial intelligence algorithm, you may even be able to not completely replace a chemical analysis, but to give at least for a certain time spent into the future, a prediction of the chemical composition of your product in the system. So after we accepted the right modesty, we need the right focus. And actually, I have to extend now a little bit what I just said 15 minutes before. For the second channel, there is also a third option. It is not only the physical separation or the logical separation of the second channel, there is also integration. And what I mean by this is shown here. So what KROHNE did together with Samsung as a valve manufacturer, we started to create an integration of sensors and actuators in one device in the field. And by that, we can cover the production and field level. We also can integrate the control level because this is a self-controlling valve. And we can also give information about the for the supervision level. We integrated here a valve, a flow meter, and two pressure and actually also temperature sensors, not shown here. We also integrated the control level because the focus-on device includes a powerful embedded computer, which is able to do local control. And with the integrated sensors and some additional AI algorithms, we're able to give also information on the supervision level, which is far beyond only the local control information. Putting that together, we end up with an integrated, actually it's almost a kind of small module. It's a localized autonomous control element which can adjust autonomously the flow at the one point at the installation, and which can provide a lot of additional diagnostic information. But local control is nice, but it's not everything. Finally, we also need right sharing, because we have to distribute your abilities wisely. And you all remember that probably, the times they are changing by Bob Dylan. And that brings me back to the slide I've shown before. That's quite old. As I told you, it's from the pre-2000 time-ish, something like that. But I added another dot, and that's the Apple M1 neural engine, but only the neural engine. And that would be somewhere here. So that's quite a nice confirmation that this trend is definitely about to continue. And that's what we have to incorporate in our considerations, especially when we think about future setups of how can a system of field devices, of edge devices, and of cloud connectivity look like. That's for the aspect of computing power. The other aspect is about communication systems. I borrowed that slide from Intel. It's not from me, and they've taken it from Northwestern University. I like it quite a lot because they predicted the data rates for 5G quite well. And they did some extensions for 7G, which is then about to come in 2040 with special features like 3 minutes for a human brain upload to a remote avatar. I like that one. Or for 13G, which is about to come in 2100, if the speed continues as in the last decades. Then we would only need 20 seconds for teleportation based on meshed implants. So it's quite a visionary thing, but I like it. It is indicating that things are changing. Coming back to our reality, we have a lot of equipments in the field. And in the future, they're hopefully connected with a powerful communication backbone, but they can be connected to an edge device, a local system, still a local system. Then we will have a cloud with a connectivity probably to other edge devices. You have certain communication bandwidths, and I'm sure there will be between 10 and 100 megabits. That's already indicated by the APL standard, but also the cloud connectivity will be more or less in the same range concerning the connectivity speed. Difference is in the latency. While your local system will come with a latency of 1 to 10 milliseconds, the latency for a cloud server is high and at least unpredictable. Even if you're able with 5G to establish low latency on average, there is no guarantee that for certain communication packages, the latency may be really unpredictable. Concerning the computation power, there's quite a difference. 2 and 4 die devices will be in the range of 1.5 megabit RAM, accordingly flash, in the range of 500 milliwatt or up to 10 watt, and have computing engines with 100 to 200 megahertz, whereas edge devices are in a much higher performance and power range. And of course, for cloud service, there seems to be more or less no limit. When we look what we can do with it, especially in terms of artificial intelligence and neural networks, we will see that the neural network performing is hardly possible on 2-wire devices in 5 years and not even in 10 years. It is somewhat possible for what we call universal 4-wire devices with limited power, And it is definitely possible with 4-die devices with high performance up to the 10-watt class. These are indications of computing performance predictions in 5 years from now and in 10 years from now. When we look at the net training, that is the training of the neural networks, it even looks worse. You can completely forget to do network training on 2-way devices now in 5 years and most likely not in 10 years. You may be somehow possible to do it to some extent on 4-wire devices, and you are able to do so already today and even more in the future on high-performance 4-wire devices. Looking at the future prediction for the network performing and training on the edge devices and on the cloud computing, there is already today, and even more in the future, no real limitation to do so. Why do I point to that? Because it gives us a clear indication that relying on 2-wire devices or 2-wire installations will kill future smartness in the field, or in other drastic words, no smart instruments in the field with a typical 2-wire installation. And you have then quite a choice to put artificial intelligence and neural networks into your overall system. You can do it in the field on 4-wire devices. You can definitely do it on edge, or definitely also in the cloud, depending on many other boundary conditions. But with such considerations, you're already today able to give a top-level prediction how a future system architecture can look like, concerning especially the usage of neural networks on different levels of the hierarchy in our plants. So finally, I have some slides to summarize the statements given in the presentation before. This one I like. Even though your brain is only about 2% of your body's weight, about 3 pounds, it uses 20 to 30% of the calories you consume. So brains need energy, power them. Coming back to the story between the 2-wire and 4-wire installations in the field. And if you want to be fast, definitely don't take the bus. And safety critical things usually need to go fast. And therefore, do not do automation control from the cloud, though it might provide the best overview. And local systems will look more and more differently in the future. So with that, I can conclude my 8-fold path. I hope I was able to make you join me on the way, and I hope you also could enjoy the way. But I have one thing to admit at the end of my presentation. You know, this Congress is meant to demystify process analytical technology. It's fine for me. But to be honest, I lied about the rainbow in the beginning. It cannot turn numbers. And infinite remains the number of our possibilities. Thank you all for your attention.
Thank you very much, Attila Bilgic. I hope you are with me still. And okay, great. So for me, yes, to your question, I could follow along, and I enjoyed it very much. I think we do have still some time for open questions to discuss. And before I jump into that, for all the participants, there is this chat function under the Converia. If you have questions, bring them here so I can then ask for you, and Attila Bilgic can then answer. I think right now, as we do not have a current question from the audience, I actually have noted myself a couple of those, and I might then give it a head start. So you have showed a very good overview along your eightfold path. But I do have one question, which is probably not so technical, but goes a little bit more into your abstract, where I could read that to actually arrive successfully that's more a question of mindset compared to technology. Could you elaborate a little bit on that?
Yes, definitely. That's a very good question. With what I mean with that is, I mean, to be honest, for going forward with all the advantages that digitalization can bring to us, I think the majority of the technology is already available. For sure, there may be gaps here and there, you will have gaps, but base technologies like right connectivity, APL is or will be available. Bluetooth is available. More and more suppliers give you a Bluetooth connectivity. There are very powerful algorithms for artificial intelligence, and there are also quite a number of startups who are eager to, of course, to learn, and also, of course, to cooperate with big corporates in the end, of course, to fuel their business, but also to provide solutions. So I think there is a lot of technologies already available, but I think the mindset of the users is still a bit too conservative and stepping back. And this stepping back, I can understand from a perspective like I don't want to sacrifice anything, especially about my it's not only functional safety, about stability, availability of my processes. So the afraid to jeopardize the safety and the availability of processes is unfortunately much higher than the expectation on benefits. That's mainly what I meant. It's more a matter of mindset, much more a matter of mindset than of available technology. And I think it's in the end, it comes back to the incentives that are given for those who are more courageous, who are willing to take steps forward. And this incentive is most likely too low.
I see. Thank you. Thank you very much. I do have a follow-up on that, a follow-up question. But before asking that, I would ask the question for Achim Ecker from the Zurich University of Applied Science. And he's, first of all, thanking you for the great presentation and is asking, could you please indicate an application note or publication describing the flow regime determination by vortex flow meters?
We didn't publish it to that extent, but there is a master thesis available. I'm free to share that.
Can you then share us that's already during the EuroPACT so we can post that?
I think so, yes.
Great, thank you. And then another question from Michael Maywald from BAM. Again, thank you. And question, will the APL be enabling technology to get rid of 420 milliamperes? And in brackets, and also 4-wire as a question.
So that's what I wanted to. Of course, I was a bit direct in my presentation, also a little bit provocating. APL has to replace the 420 milliamp, and if it doesn't do so, then we probably lose not one of the last chances. I think it will be the last chance for more digitalization in the process industry. So in that sense, I think APL is really the key enabler. Will APL get rid of the 4-wire? That's what I tried to indicate at the end of my presentation. You can eventually get rid of the 4-wire, but then at the cost of the smartness. Because if you want to have more computational power, and that is again necessary for neural networks and machine learning algorithms in the field. So if you want to have more smartness in the field, then you have to continue 4-wire even with APL. That was the key message, which I would actually highly recommend. When you ask me about personal opinion, I would highly recommend even with APL to continue in 4-wire installations, really for the main aim to empower the field. We need more computational power. Computational power will go down in cost, definitely, and it will give much more opportunities than it will cost. This was also indicated by this old graph.
Yeah, maybe prior to the next question from a participant, a brief question that from my side. As you mentioned, for the APL and the power gap that you showed, there might be some elaborations in the future, some future work on that. Do you see that those can be brought together and that we can overcome that power gap for that technology?
Definitely yes. This is a clear answer. Definitely yes. So I see it. It will be also going with explosion protection power supply. The trick will be to use the power provided through the APL communication, mainly for the communication stack, but to power the rest of the system in, for example, in intrinsical safe power. So answer is yes, can be overcome.
Okay, thank you. And then the next question is from David Littlejohn from the University of Thrustlight. And he's asking, what is required in terms of internationally agreed frameworks to allow ubiquitous adoption of the eightfold path protocols from a technical perspective?
Okay, that's of course a difficult one. I mean, let me start with a simple one. APL, it's an IEEE standard. So it is standardized already internationally, so I don't see any further need there. For many of the other aspects, there, as you could have, I think I've shown that there is quite a close cooperation between, now I'm talking not as KROHNE, as VDE. There is a close cooperation with NAMUR, and there is already quite some agreements on many of those topics. But to be honest, of course, there is also quite a number of topics that are not internationally standardized yet. This is like we have to be also honest, like NOAA is a very nice thing and I like it a lot, but it's mainly a topic of NAMUR and the member campus of NAMUR, and not so much of US American or Asian industry. Although I think with NAMUR China, there might be a chance to also promote it there. But it's still a way to go.
But and could you maybe comment on, probably from the 8 steps that you showed, which one in that sense that David was just asking is probably most important?
Most important is difficult to say, but APL is the key enabler for everything. Because for all the aspects I have shown, without either APL or something similar, it doesn't have to be APL to be honest, but either APL or something similar, you will not be able to do many of the other steps. Because first you need to have access to all the data available already in the field. I'm not even talking about installing additional equipment. I was always just talking about use all the information, what is already available, because 95% is just thrown away today with current installation. 95%, I'm sure, or even more. So reuse, use first what is available, and the key enabler for this is definitely APL, yes.
Okay, thank you. And I think from time perspective, there might be one question, and that may come from me again. So you showed us an interesting example about AI, and prior to that, you discussed the difference between safety and security. Can you just say some words with respect to the use of AI and in the safety concept?
Yes, for me, I'm spontaneously thinking there are two aspects for the use of AI. I can use AI for non-primary control purpose. Yeah, and I can use AI for primary control purpose. Why? Because I can use AI also to generate a better, more stable primary measurement value, which is used for a control function. Then you seriously have to think about also what you mentioned, the safety aspect. But when you use AI not for primary control functionality, but for additional functionality, predictive maintenance, soft sensors, non-control relevant topics, then actually it's much more relaxed, because then you only need to make sure that the AI functionality is not interfering with the safety functionality. This is something else.
Yep.
Yeah, still a challenge because you have to make sure there is no interference, but easier than the other one. And another comment going a bit into that direction is when I discussed with recently in the last weeks, for example, in Germany, PTB, but there are also other institutes about metrology. They were also on the way to think, I would say to think, not more, yeah, that also algorithms based on AI, non-deterministic in the sense like not physical. Non-deterministic is not so right, but let me rather call it not based on a physical model, might be also suitable for measurements, for critical measurements, also maybe eventually for something like custody transfer or other important measurement systems. But this is just at the beginning, I would say.
Yeah, but we will definitely see how this journey continues.
Yes.
I could continue for quite a while, but I think I'm afraid that our time is already over. So thank you again very much for your great and interesting talk. It was a great opening lecture for EuroPACT. I hope you might have the time for the upcoming 2 days to join a little bit more. And I think having a look on the agenda, we will now go into the part training sessions. And I hope that Franz Vandenberg is now with us, and he will then introduce us into the training session. Once again, Attila Bilgic, thank you very much.